We are now doing the rotational units, and the good news about rotational is there are no new major concepts here in terms of how we're going to approach solving problems. And what I'm going to show you right now is rotational kinematics, which is mathematically the exact same as kinematics. The only thing that's different are the variables. That's it. So here is one of our kinematic formulas. We've got our displacement, the x displacement, which is of course the change in x position. That equals the initial x velocity multiplied by the elapsed time plus 1/2 the x acceleration times the square of the elapsed time. In rotational kinematics, instead of x displacement, we have the angular displacement. And it is still, you could still say the x angular displacement, the idea being this is a component, so it can be positive or negative. And then we're going to have, instead of the initial x velocity, it's going to be the initial x angular velocity. And this is the Greek letter omega. It looks like a W, of course, but it's supposed to be the Greek letter omega. In print, it looks more obvious. When I write it, it's going to look like a W. Still just elapsed time. And instead of x acceleration, we have the angular acceleration. Again, let me point out these are all components, so they could be positive or negative. And then the square of the elapsed time. Now I'm only writing out one of the kinematic formulas. You can see the other ones in the homework. They're also on the formula sheet. And it's literally just that we're changing one variable for another. So when we're changing displacement to angular displacement, velocity to angular velocity, acceleration to angular acceleration. Here we're using the Greek letter alpha for angular acceleration. These are, as I was just saying, this is the same, exact same mathematically for both equations. These equations are the exact same mathematically. There's a conceptual difference because we're talking about rotation now. So here, we've got this little propeller Lego toy, and it can spin. And when I hit it, it speeds up. That's angular acceleration, and it also slows down. Now, one of the good things about rotational kinematics is we're only going to have one dimension. With regular kinematics, we had 2 dimensions. We're only going to have 1 dimension for rotational kinematics. So it can either spin, so this is clockwise or counterclockwise. That's it. And of course, which direction is positive is arbitrary. You can call clockwise positive or you can call counterclockwise positive. But of course, once you choose one direction positive, the exact opposite direction has to be negative. And if we're talking about how fast it's spinning, that's the angular velocity, or you might say the angular speed sometimes. The rate at which that's changing, that's the angular acceleration. If we go back to our basic definitions of velocity and acceleration, we would say, oh, well, the x velocity is if I'm talking about the average x velocity, I can write that formula down. Well, guess what? If we're talking about x angular velocity, again, this is the average, I'm replacing displacement with angular displacement. If we're talking about acceleration, all I'm doing is changing the appropriate variables. A becomes alpha, V becomes omega. Okay? But the conceptual ideas here are the same. Now, of course, the units are different. We're talking about rotation. If we were talking about linear quantities, we'd be measuring distances. So we'd be talking about meters per second. But here, with angles, we're talking about, well, there's 3 choices really. We could be doing degrees, we could do radians, or we can do revolutions. So there's three choices. Let me write these choices out. We've got, so theta needs to be measured in degrees, radians, or revolutions. And you use whichever one is appropriate for your situation. In this course, it's almost always going to be radians or revolutions. I don't think we ever do the velocity or the angle when we're talking about kinematics anyway in terms of degrees. Things to remember though. 1 revolution is 2 pi radians. And this is the abbreviation for revolutions. This is the abbreviation for radians. And of course, this also equals 360 degrees. In our rotational kinematic formulas, such as omega, let's see, this would be omega final x, initial x here. I'm just writing one of them down just as an example. In our rotational kinematics formulas, it doesn't matter what you use. You can use degrees, radians, or revolutions. It's just that every quantity has to use, you have to pick one, and all of them have to use that quantity. So for example, here, my angular velocities could be radians per second. Okay? So this could be radians per second. This would have to be radians per second as well. And this would be radians per square second. Okay? Or I could choose revolutions. This could be revolutions per second, revolutions per second, revolutions per square second. And if it makes sense, you don't have to use, you could change the units of time. It could be in terms of minutes. The point being, you have to be consistent. The only unit of, they all have to use the same unit of angles. So radians or revolutions or degrees. But again, we're not going to be using degrees for rotational kinematics. Or again, they have to use the same unit of time in all cases. So for rotational kinematics, we've got a lot of flexibility into what our units are. Now, there are relationships between the rotational quantities and the linear quantities, and I want to spend a little time talking about that. These relationships are, of course, listed in the content section of the homework, but I want to write them out and talk about them. They're pretty straightforward, and it all comes actually from the definition of an angle. If you're talking about what an angle is, you start with some kind of radial arm and you rotate it. And if you rotate it, that's the angle, and you're going to get a curve over here, and that's called the arc length. And it turns out you can relate these as, so strictly speaking, it's theta is proportional to S over R. But normally we measure, in this situation, mathematicians would measure theta in radians, and so they often write this just as theta equals S over R. So this is a true statement if your angle is in radians. That's a key idea for us, because from this, what you get is, let me rewrite it right here, R times theta equals S. And you can quickly see if we say, well, let's do a change in theta and let's divide this all by time. So I'd have, for example, R delta theta, I could have a delta S, and then I could say, well, let's divide this all by time. Then I quickly get this relationship. This is just omega, this is just speed. And so you get this relationship that relates the angular velocity to the linear velocity. So the idea being, something is spinning, it has a rotational velocity, but it's also covering some distance in time. So how do I compare the two, the angular velocity to the linear velocity? And it turns out, as we see here, that it depends on the radius of the circular motion for that object. So if I'm talking about the tip here, I'd need this radius. So as it's spinning, I'd need to know its angular velocity. I'd know that radius. I could figure out what its speed is. But I might be interested in a point that's, only halfway along this fan blade. So only right to there. So then I would need that radius. I'd put that there. It'd be the same angular velocity. Since this is a rigid object, every point's going to have the same angular velocity. So I'd put half of that of the overall radius, put half of that in there, times the angular velocity to get the linear speed. We can continue with this to come up with this relationship. And this, though, is only the tangential. This is the tangential acceleration. If we want the radial acceleration, we need to remember the formula for radial acceleration is v squared over r. Okay. V is r omega. So if we square that, we're going to get r squared omega squared over r. And what that ends up turning into is just r omega squared is the radial acceleration. So these give us relationships between our linear values and our rotational ones. So very useful, very, very useful. Now there's one thing left to talk about, and that's the condition for rolling. So let me talk about that. Oops. There we go. This is the condition for rolling, and it looks obviously very similar, virtually identical to this one. The only difference is the subscripts. So what is the difference here between them? It's a conceptual difference, and you need to make sure you're clear on this. This is saying that for an object that's rolling, the velocity of that object, so think a wheel, the velocity of that wheel is equal to the radius of the wheel times its angular velocity. Now, how is that different from this? Well, coming back to this is a general formula. And so this is something that's moving in a circle, but it's not necessarily the object itself, so that I'm finding the velocity of. So going back to where I was saying, well, we can look at the tip of this blade, or we could look at a point right here. And that's the idea. With this formula, we could look at any point on this blade and multiply that point's radius times the angular velocity, and we'd get its linear speed. We'd figure out how fast it was actually moving. But of course, those points, those are just points on the blade. This isn't actually the condition for rolling. In fact, this thing isn't rolling. Okay. If something is rolling, this has to be a true statement, that the velocity of the object is going to equal the radius of the object times the angular velocity. That's the condition for rolling. It's a very important condition that we will be taking advantage of in the homework problems.